Good morning. How are you doing today? Beautiful outside, beautiful inside. Hope you're beautiful over there as well. Now, I'm going on a lot of assumptions with that one. Can't actually see you. Okay, so we went over circuits, and we're going to go over some circuits a little bit more. There's a lot of stuff to do with circuits. Mostly it's just practice. Concepts are simple, but you have to think very deeply about very simple things. So a couple more concepts we're going to go over. We'll go over a few more concepts, and we'll do some problems. First concept we want to talk about is a voltmeter. So I'll start by drawing up a circuit. There we go. So here's the battery. We'll have some voltage. I'm going to call it E for EMF. EMF is an electromotive force. For all you care about, it's the same as voltage. For all most people care about in life, it's just voltage. It's just that, EMF is a more general term because it includes things like motors and generators. Okay. So a voltmeter measures voltage. And the way they are normally connected is like so, in parallel. And you also have, on the converse side, an ammeter. I'm going to draw it like so, and then a resistor, and then back. And we still have our EMF, we have our resistance R. And so an ammeter is in parallel, an ammeter is in series, a voltmeter is in parallel. An ammeter is to measure amperage, i.e. the amount of current that's flowing. So the general idea of an ammeter, without getting too crazy into it because we haven't talked about some of the concepts yet, but remember when you were a kid and you had like a nail and you wrapped it in copper wire and you ran a current through it. It became an electromagnet. Well, in most cases, an ammeter is kind of the same thing. So let's say this is north, this is south, and there's a little dial on this thing, and this thing is free to rotate, and that thing is metal, and there's copper wire wrapped around it, and we have a current flowing this way. So actually, I think I have it backwards. That's okay. We'll say the current is flowing in this direction. And so, in effect, what you've done is you've created an electromagnet out of this thing in the middle. And if it's free to rotate, and you put a little spring on it, so you get a little spring force going this way, what happens is current flows through here, creates an electromagnet with north-south, and it's going to want to align itself with another magnet on the outside that's also north-south. And it turns out, we'll talk about it later, for an electromagnet like this, the amount of strength of the electromagnet will depend on how much current is flowing through it. It depends on everything, lots of other things as well. But it'll be proportional to the current. And so the more current you get, let's see, these are just numbers to show that it's a meter. The more current you get, the more it's going to align with this other magnet. I think it's called a diarcible. I should look that up. The electromagnet they have created will be offset by a little hairspring, a tiny spring that can rotate. And so you get more current, the meter moves this way trying to align with this other magnet. And this is a measure of current, and that's how an ammeter works. Well, a voltmeter works the same way basically, except, so you have Ohm's law, I equals V over R, or V equals IR if you prefer. And if you have a known resistance, you can find the current, then you can also find the voltage. So we never actually really measure voltage per se. It's just in a different form. we always measure current, and then we can convert that into voltage. And we can convert current into lots of things. In general, when you have electric meters, the only thing that's really measured is current, which in turn you use current to measure the magnetic field, which measure current. We measure current for the most part. So one of the key parts, though, is the ammeter is in series. And so everything's going to have some level of resistance. So if we look at this on the inside, you're going to have something that looks like this with some sort of internal resistance and an amperage. So you want almost all the, you don't want the ammeter to change the circuit, because if you had a significant change in the circuit every time you measured it, then all your readings would be off. It'd be like you have an elephant that's blue, but every time you look at it, it's red. So it's like, well, is the elephant blue or red? Well, when you look at it, it's always red. So you mess up all your measurements of, elephant color and such. Same thing with an ammeter. If you had an ammeter with a big resistor and a big resistance, then every time you connected it up to the circuit, it would change the overall resistance of the circuit, which would then change the current of the circuit, which would then mess up all your readings. So the idea with the ammeter is, since it's in series, you want R equivalent. So I'm going to call this R internal. So you want the R equivalent when you connect up the ammeter. So it would equal R internal plus R, this R right here. And what you want is the R internal to be really small. That way R equivalent is basically the same as R. And then going back to a voltmeter, which again is really just measuring current, but then taking a known resistance and then converting that over to a voltage. And you notice how it has to connect to 2 points because the voltage is the difference potential. And ammeter, you can have the amp at a specific point, but voltage you need 2 points. So what you're doing is measuring the voltage across the resistor. A voltmeter, if you look at this internally, it's going to be something like, well, it's going to be exactly the ammeter. But since, and this is going to be just a slightly different drawing. So what we have here now is the same picture where I drew the R here, there, and then we have the internal resistance of the voltmeter and then another amp meter because it's going to be measuring the amps. The difference though this time is this R internal, which you can barely see this R internal is going to be very large. And the idea behind why that is because you don't want to disrupt the circuit, because every time you hooked up the instrument, the circuit changed to be the whole red blue elephant problem all over again. And so what happens then is you want R equivalent, which is, let's do, we're going to do some math. Easy math. Well, math. We're going to do a little bit of math. So for the voltmeter, it's going to be hooked up in parallel. So we'll have 1 over R internal plus 1 over R. And R equivalent, boom, boom, boom. And then if we want to solve for R equivalent, we would, we'd probably have to combine these first. So you'd have R plus R internal over R equivalent times R internal. Okay? And then this will be 1 over R equivalent. Flipping it over, taking the reciprocal, rec, REQ, that's equivalent resistance. That's just supposed to be R right there. Okay. Did I lose? Okay, nope, I'm good. Times R internal, R plus R internal. Okay, so the equivalent resistance, if R internal goes really big, hope this math works out. Otherwise, I'm going to look really dumb. Really dumb. Okay. So we factor out in R internal. We have R over R internal over R over Rn plus 1. Okay, cancel, cancel. This goes to 0, and we're left with basically R. Okay, so when we do the math, if you have two resistors in parallel, but one is super big, then it's basically as if that super big resistor didn't even exist. So if you look at this from a hydraulic analogy or people going into a stadium analogy, you have two doors. You have a bunch of people over here trying to go inside these various doors. And one door offers significant resistance. You know, it's really small. And then you have another really big door. This is supposed to show the arc of the door. A really big door probably doesn't open that way. It's okay. Just showing that it's a door. If one door has a lot of resistance to people going through, then it's going to be almost as if it's not there. If you have thousands of people going through this door, and maybe 1 per hour going through the other door, then no one's going to care that this second door really exists. And it's the same thing with resistance over here. The voltmeter is just an ammeter with a super high resistance hooked up in parallel. But since we have a very high resistance, it's not going to siphon off a whole bunch of current. And it's not really going to affect the circuit a significant amount. It will affect the circuit a little bit, but that's just an unavoidable part of life. And that is the idea behind an ammeter and a voltmeter. One of the important parts is ammeter is hooked up in series with a very small resistance, and a voltmeter is hooked up in parallel with a very high resistance. But in the end, everything in life measures amperage, current. Okay, 2 more concepts, kind of one concept, but also kind of similar. And then we'll move on to a few problems. So, Kirchhoffs voltage laws. So we have Kirchhoffs voltage law and Kirchhoffs current law. I'm going to start with Kirchhoffs voltage law because I don't know why. Either one would be fine. So the idea behind Kirchhoffs voltage law is any loop within a electrical circuit, if it's a closed loop, the change in voltage will be 0. So if we have a circuit like this, then we could start at any point. I'll choose right here. I'll choose right here, just before the battery. And we go up this direction. So when we go through the battery, we're going to see a rise in voltage because the battery provides a rise in voltage. So you could think of this as, if this is like a 9-volt battery, you start with 9 volts here, and then come up this way, and then after the resistor, then it would drop down to 0 volts. So you go through the battery and you write, that's a terrible epsilon. Epsilon for the battery, electromotive force, and then as you go across the resistor, you're going to have a voltage drop. So it'd be minus the voltage of the resistor, and then you get back to the beginning where you started, and that has to equal 0. Any closed loop around a circuit, the total amount of voltage change will be 0. So, give a slightly more complicated example, less intuitively obvious. So let's say we have something like this. We have a resistor. We have, then branches off it. And then let's say it comes down like this. And we'll have another branch here. And then like this. And then maybe we'll do another one here, just to make life exciting. And we'll have E here, and then these will all be R. Not because they need to be R, but because it's just convenient for me. But I should label them. 1, 2, 3, 4, 5, and 6. Okay. And this will be EMF 1. But I drew it wrong. There we go. There we go. Okay. So now the question is, does the same concept hold true based on what we went through here? So let's choose a path. We'll go this path like that. So then we could write, I'm going to start just before the battery though, just more convenient. And we're going to choose the direction of current here. So we're going to say current goes this way. I assume it does. These are currents. And these, even though I label all these currents I, they'll actually be different currents in different places. Because when you branch off, the current will branch. Okay. So start here. For the first loop, we'll have epsilon minus, and then I'm going to call voltage R1 minus, and then go through 3, voltage R3 minus voltage R4, and then we get back to the beginning. Okay, and we'll do another loop. We'll do one like this. Epsilon minus voltage R1 minus voltage R6 equals 0. Okay? And then we'll do another loop. Let's do up this way, and then over here, and then back to the beginning. So then we'd have epsilon minus voltage R2, no, voltage R1, then minus voltage R2 minus voltage R5 equals 0. Okay, and we can do this again and again and again until we have enough variables that we can then solve the equation. So you might think, well, okay, I have all these voltages, but they mean nothing to me. Yes, mostly true. So what we do then is we take these voltage drops across resistors, and you can rewrite it in terms of Ohm's law, or V equals IR. I prefer, though, I equals V over R. But in this case, it's easier to rewrite it, to rearrange it. And we would take the current, so this one would be I1 R1, where current is the current that's passing through there. And you might think, well, is I1 the same as the other currents, or is the same current throughout the whole thing? No, not necessarily. So if you look at this, so this would be I3 R3, this would be I2 R2, this would be I4, ooh, that was terribly written, I4 R4, and then each of these might have a different amount of flow through them. This is where the hydraulic analogy really works pretty well to help intuitively understand what's going on. So the way the hydraulic analogy works is it says, all right, instead of having batteries, you have pumps, and batteries maintain a differential pressure voltage between them, between the top part and the negative part, positive plate and negative plate, while a pump maintains a set amount of pressure. We're talking centrifugal pumps here, not positive displacement. The positive displacement are, oh gosh, I opened up a larger can of worms there than I meant to. A positive displacement could represent a constant current flow, where centrifugal pump would represent a constant differential pressure. Okay, focus, back on track. So you have a pump right here, and then you have some sort of resistance. It could be like a filter, it could be a valve, it could be whatever. And then you have a pipe leading off to it. So the water is going to come up through here. Some of it will go down here. Some of it will go over there. And then it goes through some more filters. Some water will go through here. Some water will go through there. In the end, the water will come and join back up. Well, the amount of resistance to flow is normally going to be related to your volumetric flow rate, how much water is going through there, which is kind of related to current. So the amount of pressure drop across each filter is going to be related to how much water is flowing through, but then also how difficult the filter is to get through. If you have a very fine filter or it's a very clogged and dirty filter, then it's going to provide significant resistance. And then the idea then is the water will flow through, and then you're going to get pressure drop. And if you do any loop, you have the same idea as a Kirchhoffs Voltage Law, where in the end you're going to have the same difference in pressure constantly. And when we write voltages here, we normally write 0 on one side of the battery and like whatever the voltage is on the other side. So with our very simple example, we have something like this, and we have like a 9-volt battery here and like a 3 ohm resistor. Well, we normally write 9 volts here and 0 volts here. Well, voltage really doesn't mean 9 volts and 0 volt, it just means a difference of 9 volts. So you could just as easily, I'm going to find the current real quick. So I equals V over R, which equals 9 over 3, which equals 3 amps. So we have 3 amps here. Well, we instead of saying 9 on top, we could say 12 volts and 3 volts. And that would be just as valid. And your thought would be, well, wait a sec. Our I equals VR doesn't work anymore because we have 12 divided by 3, which is 4 amps. Now we have more amps. That's not true. So this, even though it's written as a single value, V, voltage, it's really a difference. So what we did previously was 9 minus 0 divided by 3 equals 3. And so this time we'd have to do 12 minus 3 over 3, which again gives us 3 amps. So it's the difference that matters, not the absolute values. And yep. And that's kind of the idea of the hydraulic analogy. Don't take the hydraulic analogy too far. It's really great, and it gets you correct answers to relatively simple problems. If you're talking about resistors, batteries, and capacitors and inductors, which we'll talk about later, then the hydraulic analogy is great. Go for it. Yep. I think I got most of the concept. So the idea with Kirchhoffs voltage law is any loop, it will end in 0. You'll have the if you write all the voltage rises, pretty much batteries, or if you're going the opposite direction of current, then it would be considered a voltage rise as well. Then the end of that loop will give you 0. And we'll do an example later to kind of show how that works. The other one was Kirchhoff's current law. I know you're thinking that, wow, that was a lot of information for the Kirchhoffs voltage law. How difficult is Kirchhoff's current law going to be? It's a lot simpler. Well, equally simple. The point here is all the current going through or from a node will always equal 0. Draw an example. So we have our, let's do a resistor. And we'll do another resistor here. So we'll say this is resistor 1, that's resistor 2. I'll call this resistor 2 and this one resistor 3. Just to kind of, you'll see. You will understand. So the idea with Kirchhoff's current law is all the inputs have to equal all the outputs. So let's say this is current 1 right here. This is current 2 because it goes through resistor 2. And this is current 3 because it goes through resistor 3. So this is saying that current 1 equals current 2 plus current 3. Everything that comes in has to go out. This works well with a hydraulic analogy as well, because if you have a pipe and it splits off, it's not like you're going to magically get more water. So the currents at any given node, any point, has to sum up to 0, where the inputs are positive and the outputs are negative. Okay, so that's ammeters, voltmeters, Kirchhoffs voltage law, and Kirchhoffs current law. So now let's try a problem. Okay, so this would be this like a free response type problem that you could see on an AP exam. Delicious, wonderful. Okay. Ooh, I think that's supposed to be a closed circuit. Oh, make it black so it doesn't stand out too much. Oh, that's a surprisingly straight line. Well done. Okay, student performs an experiment to determine E, electromotive force. Electromotive? I think it's electromotive. And an internal resistance R of a given battery. So batteries have internal resistance. Everything has resistance, so batteries are no exception to life. The student connects the battery in series, as shown, to a variable resistance R, also shown. The little arrow means variable. It's like a dial that you can turn up and down. How would you turn dials? I don't know. Probably like this, like a knob. Okay. With a voltmeter, right there, across the variable resistor, as shown in the figure above, and measures the voltmeter reading V, okay, as a function of resistance R. Big R, probably part of the, resistance, as part of the variable resistor R. Okay. The data are shown in the table below. Okay, multiple trials, multiple resistances, resistances. And then the inverse. Oh, those inverses are ominous. Okay. And you get like maybe 15 minutes for this problem. So I'm going to move kind of slow. Just because I talk out loud and I think out loud, where on AP exams it's generally considered polite if you do all your thinking internally. So, A, derive an expression for the measured voltage V. Express your answers in terms of resistance, epsilon, and R. R is resistance. Physical constants as expression. Okay? So we're going to do Kirchhoffs voltage law. We'll start here. We'll do a circle, and we'll come back to there. So we have epsilon as we pass through it, minus voltage R minus voltage big R equals 0. Okay? Now, they want us to get rid of the voltages here. So we'll rewrite this as E minus I, which is a current, little r, minus I, which is a current, big R equals 0. Since this is just one loop, and we assume that the voltmeter has a very high resistance, internal resistance, like it's connected with a resistor right here, which is super big, therefore we're going to assume no current goes through it. So there's one current that goes through the circuit, which is why I can write I as 1I as opposed to I1 and I2. Okay? And then I'm going to write an equation. We can find this resistance, find this current. So, So if we redraw this circuit real quick as battery R equivalent, and then back, we have an epsilon here and an R equivalent up there. And so we could take this R equivalent, and we know that R equivalent equals R plus R. Yes. And therefore, we have I equals V over R. My notation with epsilon and V kind of gets intermixed. I mean the same thing. which is epsilon over R plus R. So we're going to take this I, which we know is the current, and we're going to plug it into our equation down here. Hopefully everything doesn't cancel out and just give us 0, which would mean that I probably did something wrong. Oh, this is going to be 0. It is going to be 0. And once again, I have failed you. Okay. Oh, wait. So yes, everything does kind of cancel out to 0, which means that not quite the right path. So I'm going to back up slightly. So we're looking for V, which is the voltage drop across R. So I can rewrite this as VR, which is voltage drop across the resistor R, E minus BR. Is that true? That's true. Okay. And so now I'm just going to rewrite this portion, the internal resistance, in terms of I little r, which equals I minus, or epsilon minus, let's see here, this is epsilon R plus big R times R. Okay, so the question asks that we write the measured voltage V, which is the voltage drop across R, right here, as in terms of the variable resistance, big R, check, epsilon, check, and little r, check. Okay, so rewrite this. Voltage R equals epsilon 1 minus R over R plus R. Okay, so to backtrack what we did here, so we used Kirchhoffs Voltage Law to make a loop. We then took that loop and solved for the voltage drop across R, which is what we wanted. And then we used an equivalent resistor to find what the current would be through this system, current I. We used that current to expand the voltage drop across the internal resistor, right here. And then we rearranged things to get something that was presentable. No, want some blue for contrast. There we go. And that was what they wanted in terms of the constants. Okay, I'm good at that. Yeah, it's just math. It's one of those things where you think about, like, wow, how would I have known to do that? Sometimes you don't. Throw everything in a box, you shake it up, look to see if it's correct. If it's not, then you keep shaking. And what I did was I kind of went down here and got 0 because I expanded one of the terms that I wanted to leave unexpanded. Okay, moving on. It's really easy to get stuck on these. Luckily on the AP exam, you really only need like 60%. So I'm not saying you should aim for 60%, but a little bit of failure is okay. It's within tolerance. Okay, rewrite your expression from part A, check, to express 1 over V and 1 over R. Okay. So, more math. So I'm going to go back, I think. How do I want to do that? So I'll go back a step. 1 minus epsilon R over R plus R. And now it might be easier to take some of the reciprocals. Is it easier to take the reciprocals? Maybe. Because because I really don't want to take the reciprocal of this, because it's not like you can't just take 1 over VR and then 1 over, so you can't just do something like this. That's not allowed. It'd have to be over the whole thing. So what I'm going to do is I'm actually going to go back up here and I'm going to say VR equals epsilon, and I'm going to combine, so this is going to be R plus R over R plus R minus R over R plus R. Sounds like a pirate. And then we're left with R plus R minus R. Just switch the R's and then combine. These go away, and we're left with epsilon R plus R with an R. Okay, so we have the same equation, just written in such a way that it'll be easier to take the reciprocal. You see how this is more just math and algebra than physics at this point. Disappointing. All right, so then 1 over VR equals 1 over R plus R over epsilon. Okay, I'm going to rewrite this part. 1 over R epsilon, R plus R. Okay, so we go back to this, and then we split it up. So this is the same thing as R over R epsilon plus R over R epsilon again. And this gives us 1 over R over epsilon, plus, these cancel, 1 over epsilon. Man, this would be a good motivator to do well on the multiple choice so that you don't have to do as well on the free response. Okay, so now that we've spent the vast majority of our time trying to do the algebra, now we can reap our rewards. Okay, so I'm going to come over here and rewrite our two expressions. Can I just copy paste? Or select and drag? Haha! And then rotate so that it's very nice. Okay. Rewrite your expression from part A to express 1 over V as B. Okay. Now I'm going to clean up the board a little bit. Okay. Now, board's cleaned up, and here's the second part of the problem. On the grid below, plot data points for the graph 1 over V as a function of 1 over R. Clearly scale and label all of the axes, including units as appropriate. Draw a straight line that best represents the data. Okay. So before we get too carried away, we got to determine what the axes are, because if we choose poorly, then our life will be significantly more difficult than it has to be. So they're trying to look at 1 over V and 1 over R. I think it's variables. So what we're going to do is we're going to say, well, this right here will kind of be Y, that'll kind of be X, this will be M, and this will be B. So we have something of the form Y equals MX plus B. More importantly, this will be the x-axis, and that will be the y-axis. And so we have already 1 over V and 1 over R. So this will be X, and this will be Y. And we will plot them on this graph. I have faith in your graphing abilities, so I'm going to quickly go through and plot it. Okay, so now we have the plots graphed. So we have 1 over R. Ooh, I didn't even label the axes. Went to all that trouble to find out what the axes were going to be. Don't even label them. 1 over V and 1 over R. So I just took, so the bottom axis went from 0 to 2. So I just said each one was 1/2. And the y-axis, 1 over V, goes from, I don't know, I'm going to say 0, but basically 0.1 to 0.2. So basically in this range. And I graphed them, and those are the dots. Then I'm going to connect the dots, as they say. Come on, line, cooperate. Yeah, that's good enough. And I'll change it to blue. Ooh, turquoise. Teal. Minimize the thickness. Close enough. Okay. Maybe that is close enough. Good for me. Good for me. Okay. On the grid below, plot the data point, blah, 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 blah. Axes, units as appropriate. Oh, I guess I should include units. 1 over R. Or so it would be 1 over ohms. And this would be 1 over volts. Okay? Clearly scale, label all, blah, blah, blah. Draw a straight line, represent the best. Okay. Straight line drawn. I really despise, as a personal note, graphing. It takes so much time, and it's such a small amount of knowledge demonstrated. Frustration. And it's also very error prone, which I also like. I don't like errors. Okay, use a straight line from part B to obtain values for the following. Okay, so epsilon, okay, so we have, for our equation, B, which is the y-intercept, will be 1 over epsilon. And then we have M, which is the slope of the line, will be R over epsilon. So if we find epsilon, we can then find R. So if we look at our y-intercept, it'll be right here. So we find the y-intercept, which is, let's see here, I can probably just count it. So we got 0.05, 0.06, 0.07, 0.075, I'll say 0.08. So, probably should actually check my line real quick. Whoop. Yeah, maybe lower that slightly. I'm going to say that's good. So 0.08. Okay. Pen activate. So the y-intercept is 1 over epsilon, which is 0.08, and this is 1 over volts. And so epsilon equals 1 divided by 0.08, which is going over to Wolfram. Let's see, they wanted to find us epsilon. Yep, okay. 1 divided by 0.08, and that gives us 12.5. Maybe. Okay. Epsilon is about 12.5, which then gives us a sorry, I'm going to look real quick. So if we look at the one that's closest to, I'm going to try 0.0, because here's a drop of 2, there's a drop of 4. I'm going to say I'm going to try another number real quick. 0.09. Gives us about 11. Yeah, I'm good with that. Okay. Be about 11, between, it's probably going to be closer to about 12, I think. Just because I think I plotted things a little bit too low. Not a big deal. Concept. We're going with the concept here. And so then the slope equals R over epsilon, which equals y2 minus y1 over x2 minus x1, which equals, going back up here, we'll just take two of the values. So I'll say that we have 2, try and get this big, there we go. So we'll have 2 minus 0.1 over 0.179 minus 0.088. 0.088. Okay, and then that was, oop, I got those reversed, upside down. So it's rise over run, the y value is 1 over v. That's okay. I know this is terrible, but then I'm just going to reverse it like that. So this number here is going to be 1.9 over 0.179 minus 0.088. Okay. 1.9 divided by quantity, 0.179 minus 0.088. And we have 20.8. Okay. Epsilon over R equals 20.8. Therefore, R, I guess this is actually the small r, not the big R. Epsilon small r, R equals epsilon over 20.8. So then we'll do 12 divided by 20.8. Divided by quantity. And we get 0.57. And then that is ohms. Yeah, it seems fair enough. Okay, and this will be R. I know it's sideways. So we have 12 volts. I'll say 12 volts. And maybe 12.5. Did I do 12? I'll say 12. So this is 12 volts. And then the small resistor is 0.57. 0.57 ohms. Okay. Now I know that was a lot of work, but trust me, it's worth it. Okay. Using the results from the experiment, calculate the maximum current for the battery. Okay, so current is delta V over R. And in this case, the voltage of the battery will be 12 over 0.57, which would be about double, which would be about 25 amps. So, yeah, 25 amps. I'm good with that. Okay, a voltmeter is to be used to determine the electromotive force of the battery. After removing the battery from the circuit, 2 voltmeters are available to take this measurement. One with a low internal resistance and one with a high internal resistance. Indicate which voltmeter will provide the most accurate measurement. Okay, so this is talking about voltmeters in general. And so a voltmeter, you'll want it to have a very high resistance because voltmeters are attached in parallel. So this is a voltmeter in parallel, and so you don't want it to, you want to have very little current going through it. And then there could be a battery here. Oh, they said they removed the battery from the circuit. Either way, voltmeters are going to have a very high resistance for them because you don't want any flow. If you have flow, it'll affect your measurement. And so you'll want a very high resistance. And just by the answer, voltmeters are connected in parallel to so as not to disrupt the circuit by measuring, you want to have a high resistance so that there is very little current flow through the voltmeter while taking the measurement. Okay, I know that was a fairly in-depth problem. Some of these are brutal. I'm not going to lie. This is the physics AP exam. No joke. Okay, got one more problem. We'll go through it reasonably quickly. We'll go through that one next time. This is the sort of problem you can kind of expect. You're probably going to get something kind of like this. You're probably going to get one graphing problem. Do your best. None of the problems are hard on the AP exam, but you just don't have a whole lot of time. So you go through, you take all the data you can, write down as much as you can think of, shake up all the variables, try and get the right things to fall out, and then graph them. Best thing you can do, just practice as many problems as you can and get kind of a feel for, especially graphing, how to manipulate the equations and graph things to get what you want. That'll be it for this one. I will see you next time with some more circuits practice. Thanks.